Hello everyone. So we have discussed about interference of the waves, and we have come across the detail that constructive interference takes place and destructive interference takes place alternately whenever we have the two waves which are trying to superpose each other at a given point or a region. So whenever two or more than two waves, whenever they try to superpose each other at a point or a region, the redistribution of energy just takes place, and due to which the total energy of the two waves is just redistributed between the dark and bright fringes whenever we talk about these light waves. Now we will discuss how to derive the formula to find out the width of these dark and bright fringes, right? So for finding out the width of these dark and bright fringes which are produced due to the interference of the light waves, two or more than two light waves, so we start with this experimental setup. This experimental setup, it is called as Young's double slit experiment. There must be a condition which must be satisfied by the light waves which are going to superpose each other, or we can say which are just interfering with each other, right? The condition is that these two light waves, they should be coherent, and two light waves can be coherent if they have same wavelength, same amplitude, and same phase, or they have the same phase constant phase difference. Either they have same phase, or they have a, if they have a phase difference, this phase difference should remain constant, it should not change. If two light waves possess these properties together, which properties? They should have the same wavelength, they should have the same amplitude, and they should have same phase. If they are not having the same phase, then they should have some constant phase difference. Then these two light sources are, or we can say light waves are called as the coherent one. Such light waves are possible only whenever the sources which are emitting these light waves are coherent. They are also said to be coherent according to the light waves they send. If they send, the two sources send the light waves of same wavelength, same amplitude, and same phase or constant phase difference, the sources are said to be coherent. Okay, so that means for the we can say proper interference, which is called as sustainable interference, in which the dark and bright fringes are not moving, and bright fringes are completely bright and dark fringes are completely dark, a kind of interference pattern which is received on the screen, it is called as sustainable interference pattern. So in order to get a sustainable interference pattern, due to the interference of the light waves, the two light waves should have the same wavelength, same amplitude, same frequency, and same phase, or a constant phase difference. So such a kind of sources which are required in order to understand the sustainable interference and the width of these dark and bright fringes under this topic of Young's double slit experiment. So practically it is not possible to have the two different sources to be coherent, because howsoever small it may be, there will always be the difference in the wavelengths or frequency or phases which may not remain constant, right? So therefore we can never get the two sources which are coherent. So in order to come to this situation or create this situation, what we do, we take one source of the light and place two slits in front of this source. Forget this single slit. The source is illuminating the two slits now, right? Two slits means two openings. Now the light is coming from these two openings. So after these two slits, whatever the light is coming, these are the two light waves of same wavelength, same frequency, and same phase or constant phase difference. Now from the single source, this is how in Young's double slit experiments we receive the two light waves of coherent nature. So that's why this experiment, it is called as double slit experiment. Now these two light waves, after coming out from these two slits, they just interfere with each other and create a redistribution of energy. And if we place a screen in front of these slits, we get a pattern of dark and bright fringes, where the central fringe is bright fringe and alternately dark and bright fringes are formed. So we can place the screen at a particular distance from this double slit setup, so as to form the pattern of more width or more intense light, right? Let us now proceed to derive the formula for the width of the fringes, whether it is the dark fringe or it is the bright fringe or it is the central bright fringe. Okay, the conditions for the formation of dark and bright fringes we have already understood, right? So here it is the situation. Here is the source which is emitting the light of particular wavelength, particular frequency and particular phase. Now we are placing a setup of two openings, or we can say slits, S1 and S2. These are the two openings or slits from which the light can come. Whatever light is coming from source S1, it is in coherence with the light coming from this slit called as S2. So these lights are now having the coherence with each other in terms of their same wavelength, same frequency and same phase. Now these two light waves interfere with each other and reach at every point on the screen. At the very central point of the screen, we get a bright fringe. Bright fringe means bright spot where light is illuminating the region. And then we get alternately dark and bright fringes on the both sides of this center of the screen. We are taking that these two slits are placed at a distance d from each other, means the distance between the two slits is small d, and the distance between slits and the screen, this is capital D, right? So this is the center of this distance d. So above half it is called as d by 2 and lower half this is also called as d by 2. This is necessary in order to understand the derivation properly. Now we take any point P on the screen. This may be the point for a bright fringe or it may be the point of a dark fringe. We will take that later by applying the condition for that particular dark and bright fringe. We take that we have a point P where the light coming from S1 and S2 is interfering, right? So the light coming from slit S1 and S2, they do not travel equal distances. They travel different distances. The light coming from source S2, it is covering more distance than the source light coming from this source or slit S1. So how much extra distance the light coming from slit S2 is covering, this can be known by this derivation, for which what we do, we draw perpendicular from S1 on this line S2P. It should meet somewhat here, just as this. So we are drawing perpendicular from this point S1 on this line S2P, right? So this is the extra distance. This is the extra distance which the light coming from source S2 take in order to reach point P. So therefore, what is this path difference? Path difference is nothing but the difference of the paths which are traveled by the light coming from source S1 and S2. So what is the difference of their paths? So it will be given by delta. It is equal to S2P minus S1P. So whatever left, it is the path difference. So here we do just some mathematics and derive the formula. So what we do? We start with this, we can say expression S2P square minus S1P square. What is S2P? It is the diagonal for the triangle S2P and this point. In this triangle S2PA. S2P, it is nothing but its diagonal, or we can say it is the hypotenuse, and also S1P, here S1P, it is nothing but the diagonal, or we can say it is the hypotenuse of this triangle S2PB. So we are taking their squares so that we can use the Pythagoras theorem. So we start solving from this expression for the path difference, which is S2P minus S1P. So S2P, we write its value, S1P, we write its value also. So S2P, it is nothing but PA square plus S2A square. So this point P, it is supposed to be at a distance y from the center of this screen. This length OB, it is half of the distance between the slits, so d by 2, and the lower half it is also equal to d by 2. Now we have to substitute the value of this perpendicular, which is PA for S2P. First we are writing the value of S2P. So S2P square, it is equal to PA square, which is equal to y plus d by 2. So this distance is d by 2. So PA is equal to y plus d by 2 square plus S2A means d square. So this is what we are writing here in this triangle S2PA. So in this triangle S2PA, we are writing the Pythagoras theorem. And from the Pythagoras theorem, we are substituting the values for S2P square. And similarly, for other triangle S2PB, we substitute the value S1P square. Right? So S1P square, it will be equal to PB square, which is y minus d by 2 square plus S1B, which is again equal to d square. So therefore d square plus y minus d by 2 whole square. So we just has substituted the values of S2P square from triangle S2PA and S1P square from triangle S1PB and nothing else. So we are just substituting the values for both the values, and now we are going to just simplify this. So on the left hand side, it is nothing but a square minus b square. So it becomes a minus b into a plus b. And on the right hand side, we will be left with only this 2y into d, small d. So this is the only thing what will be left. All other things will just cancel out. So from here, point P remains close to point O, the center of the screen, and the distance between the slits is very small in comparison to the distance between screen and slit. So for that purpose, S2P and S1P both are very nearly equal to D. So this is the approximation actually. S1P and S2P remain very nearly equal to D, the capital D, the distance between slit and the screen. So therefore, in place of these two, S2P, we are keeping approximately D, and S1P, this is also approximately D, so it becomes 2D. And this S2P minus S1P, it is nothing but the path difference which we are willing to find out. So it is delta into, this is delta into, this is 2D, which is equal to 2y into small d. Remember, small d, it is the distance between the two slits, whereas capital D, it is the distance between the screen and the slits. So here, from here, when we solve this, 2 just cancels out, and the path difference delta, we get it to be yd, y small d divided by capital D. So this remains the formula for the path difference, right? This is the general formula. Now we apply the conditions for constructive and destructive interference in order so that point P is a bright fringe, or point P, it is a location of dark fringe. So from there we can find out the distance of dark and bright fringes from the center of the screen. For that, we start with the condition for the bright fringe. That means if point P here in this diagram, if point P, it is the position of the bright fringe, then what is the condition for this path difference, which we have already discussed in our previous class? So the path difference, it should be equal to n times lambda, where n is nothing but 0, 1, 2, 3 and so on. This is an integer number. So the path difference which we have found here, yd upon capital D, it should be equal to n times lambda. So this is the condition. This is how we apply the condition for the path difference. Now we can solve this for finding the distance of all the bright fringes which will be formed on the screen here, right? Which will be found on the screen, because we point P, it may be anywhere, but we are applying the condition for the bright fringe here. So therefore we are getting the positions of all the bright fringes which will be formed. So from here, y means the position, here y the position, this position for the bright fringes, it will be given by lambda n times lambda capital D upon small d. So this remains the formula for the constructive interference, or for the position of all the bright fringes, right? Now we can find out the position of the first bright fringe, second bright fringe, third bright fringe by substituting the value of n. The value of n begins from 0. So by substituting the value of n, we are getting y to be 0. That means we are finding the position of the central bright fringe. So that simply means what we understand from here. For n is equal to 0, we are getting a bright fringe at y equal to 0. So that means at y is equal to 0 means at the center of the screen. So at the center of screen, we are getting a bright fringe. So this is what this substituting value of n is equal to 0 mean. Similarly, substituting values n is equal to 1, we get the first bright fringe which is on one side. Just as you can see in this diagram, this is the central bright fringe, then we have a dark fringe, then this is the first bright fringe on one side. This is the first bright fringe on the other side. This is the second bright fringe on the one side, and this is the second bright fringe on the other side. So we will get the bright fringes on both the sides. So y is equal to 1 gives the first bright fringe on the one side. Similarly, for n is equal to 2, we get the second bright fringe, and similarly for n is equal to n, we can just generalize the result to write the formula for the nth bright fringe. So during the question, if we have to calculate the position of any we can say number of bright fringe, we just can calculate its distance from the center of the screen by using this formula. Now we take the discussion a little further by applying the condition for the destructive interference. This destructive interference will produce a we can say dark spot, or we can say the place where there is destructive interference means there is no energy placed, right? So this path difference, as we have calculated in this article in journal, this path difference, this will be equal to 2n plus 1 lambda by 2, 2n plus 1 times lambda by 2. This is the condition for the formation of the destructive interference. So when path difference, which is found to be yd upon capital D, it is equal to 2n plus 1 times of lambda by 2, where n goes from 0, 1, 2, 3. We get at that position, we get a, for this path difference, we get a dark fringe. So therefore, the position y of those dark fringes can be just calculated by using this formula. So we are finding y from here. So y, it is nothing but d, capital D goes to the other side and multiplies, and small d just divides as here, right? So y, the position of all the dark fringes, is given by this expression, right? Now by substituting the values of n, 0, 1, 2, 3, we can calculate the position of the first dark fringe, second dark fringe, third dark fringe, and so on, or any number of dark fringe. So for n is equal to 0, what we get when we substitute n is equal to 0, we just get lambda d upon 2d. This is the position of the first dark fringe on the either side, distance of the first dark fringe on the either side, on one side, right? So at this position, the first dark fringe will be found. And similarly, for substituting n is equal to 1, we get the position of the second dark fringe. Similarly, for n is equal to 2, and so on. And in general case, we can just write the expression for the position of nth dark fringe, which will be given by yn dash, which is equal to 2n plus 1 d lambda upon 2d, which is the same formula here. So this is how we find the position of bright and dark fringes. But we just started discussing the expression for the width of the fringes. Now from this positions of the bright and dark fringes, we can calculate the width of the bright and dark fringes. For that, one must understand that between any two bright fringes, it will be the dark fringe, and between any two dark fringes, it will be the bright fringe. So from there, what we do, we take the difference of positions of the two successive bright fringes. It will give us the width of the dark fringes, because in between there there will be a dark fringe. In between the two bright fringes, there will be a dark fringe. So for finding the width of the dark fringes, what we just do, we find the difference of any two successive bright, the difference of the positions of any two successive bright fringes. So for example, if one bright fringe, it is located at nth position. So nth position bright fringe, it is its distance from the center of screen is yn, and just before it is yn minus 1. So we find the difference of these two positions here, right? So we find the positions of any two successive bright fringes. So when we substitute the values yn here and then yn minus 1 here and find the difference, we get this formula. So it will be d lambda upon small d. So this will be the width of all the dark fringes, because if you try to find, because this is the difference of all the dark and bright fringes in general. So we are finding the difference of the bright fringes here. So if you find the difference of the 4th and 3rd, 5th and 4th, or 10th and 9th, right, you will get the same formula always. So this will be the width of all the dark fringes here in case of interference of the light waves. Similarly, we can find out the width of the bright fringes. So width of the bright fringes, it is given between the positions of the two successive dark fringes. So these are the dark fringes. So in between any two successive dark fringes, for example, 1st and 2nd, 4th and 5th, just like that. So between any two successive dark fringes, there will be a bright fringe. So in order to find out the width of that bright fringe, what simply we do, we just find the difference between the positions of any two successive dark fringes. For example, yn dash, then its successive or just previous dark fringe will be yn minus 1. At this will be the position of the previous width dark fringe. So when we find the difference of these two values, we again get the same formula, which is d lambda upon small d. So that means all the dark fringes and all the bright fringes will be of same width in case of interference of the light waves coming from the two coherent sources. So that means expressions for the fringe width shows that fringes are equally spaced on the screen. So this is all the discussion about the expression for the fringe width. Now we can just plot a graph for the intensity of the light which is redistributed on the screen. So this is the center of the screen, and along the vertical we have intensity. As we move at the center of the screen, we have the maximum intensity of the light, means the intensity of the light is highest. So that means at the center of the screen there will be a bright fringe, right? And also because all the dark and bright fringes are equally spaced, or they are of equal width, so that means we will find the successive dark and bright fringes at equal distances. So at the center of screen we have a bright spot, therefore the intensity of the light is maximum, and as we move away from the center of the screen, the intensity goes on decreasing, and at this point we get a dark fringe where the intensity becomes minimum. As we start moving away from this, a little more further away from this dark fringe, we again get the more intense light which is at the first bright fringe. So here it will be the first bright fringe, and when we move even more further, we get the second dark fringe. So as we keep on moving, we get alternate bright and dark fringes. So therefore from here, from this pattern, it must be clear, or it must be understood that the intensity of all the bright fringes is equal. That means in case of sustainable interference pattern which comes or which arise out of the two coherent sources of the light, is that the intensity of all the bright fringes will be same and the intensity of all the dark fringes will be 0 for an ideal, or we can say sustainable interference pattern. So this graph must be remembered whenever interference of light is discussed. Suppose that the two interfering waves have the same amplitudes, because intensity depends upon the square of the amplitude. So maximum intensity, it will be directly proportional to A plus A, as we have already discussed, to the square. And the minimum intensity, it will be, this is the maximum intensity, so it becomes just proportional to 4A square from here, if the two interfering waves has the same amplitude. and if they interfere destructively, then the intensity will be a minus a to the whole square, which will be 0. So minimum intensity for a interference pattern, whenever the two interfering waves have the same amplitudes, then the maximum intensity will be given by 4a square, and minimum intensity will be 0, which will be for the dark fringes. So how we can achieve the sustainable interference pattern? So here are the conditions for the sustainable interference pattern. We can sum up these here. The two sources producing interference, they must be coherent, as we have already discussed. The two interfering waves must have the same plane of polarization. They must have the same plane of polarization, means they must be producing the light in the same plane. The two sources must be very close to each other. They must not be at a large distance, otherwise the interference pattern we will not be getting it. The two sources must be very close to each other, and the pattern must be observed at a larger distance to have sufficient width of the fringe width. That means from the slit, the distance of the screen, it should be large. Only then the width of the slits will be clearly visible. So this is the another condition. Next one is that the sources must be monochromatic, that the two sources must be emitting the light of single color, right? They must not emit the light of different colors at the same time. They must have, there must be only one wavelength of light which is emitted by a source. Otherwise the fringes of the different colors will be overlapping, right? Okay, and the last condition is that the two waves must have the same amplitude, because if they have the same amplitude, then the bright fringes will be completely bright and dark fringes will be completely dark. So in that case, whatever pattern we will see, it will be very clear and called as sustainable interference pattern. So that is all about this condition for the sustainable interference. Thank you.